Hello guys, welcome back to MedZone African Motives. This is hydraulics, still on the hydraulics actually, but we want to talk about the hydraulic pumps. So that is going to be our introduction. We shall see how to answer typical questions like this one that we have, but just gonna have a basic introduction, just like our hydraulic press. All right, we were talking about the hydraulic press, if you still remember. So that is one and the same thing. All right, so in actual sense, a hydraulic pump is actually used to transmit, maybe we are talking about a liquid. All right, to transmit a liquid vertically, or you can transmit horizontally, but it must be a transmission of the liquid, all right, vertically, horizontally, or against any pressure that you might be given. Taking a closer look of a pump of this nature, just a sketch, guys. You know, these things of our drawings, they are very, very complicated to some of us who are into mathematics, but something of this nature. Here, let's say we've got something like this, and here we're gonna have the point A, and also we're gonna have our point B. That is here gonna have the valve, which is the liquid delivered at a certain pressure. Then here we have our plunger on this side. So on this side here, you'll be talking about the plunger, where we have got the piston, in this case, the piston plunger. And this side, we have the pressure, in actual, the liquid. We are talking about the liquid this time, delivered at a certain pressure. So here you have a certain liquid, the liquid delivered at a certain pressure here, at a certain pressure, at a certain pressure. All right. Then here you'll be having the liquid to the reservoir, that is to the reservoir in this case. All right. In actual sense, that is the idea of what is happening here. So the liquid can be transmitted, that is vertically, horizontally. So the volume of the liquid transmitted has got a weight due to the gravity. We know that. And the liquid must be transmitted over a certain distance or height. When the force is moved over a distance, the work is done. Remember, work is force times distance. So when a force is being moved over a certain distance, we know that work is done. That's work is equal to force times distance. And this is the major part of our hydraulic pump, this part of the work done. All right. So we can talk also of the centrifugal pumps, piston pumps, or potential energy, which is available due to the relative height of the liquid, is used to deliver liquid at a pressure. That is the idea of what your pumps. Okay, so it's not much that you need. We just need to understand what are the formulas and so forth. So what is happening here is that when the plunger moves upward, all right, the valve A opens, whereby here at this point A, whereby we put our valve here, so it opens, and that of B, it closes, and the liquid is sucked from the reservoir. That is because this one is open, so the liquid is being sucked, taken from what? From the reservoir. When the plunger moves down, when this is moving down, what is happening now? A is going to close. When this closes, B opens up. All right? And the liquid is delivered now at a certain pressure. That is the principle of operation of this. Okay, in a simple situation, water is only delivered when the plunger goes down to secure a more regular stream of water. That is, we talk about the 3-cylinder single acting pumps are used on that condition. So we shall talk about the number of cylinders, but mostly a 3-cylinder is used to secure this. All right, so that is in this case to secure more regular stream of water. If you want to secure a more regular stream of water, you have to use what? A 3-cylinder. That is, we shall talk about this in our calculations when you are referring to the number of cylinders and this and that. All right, but for the calculations, this is what you're going to need. One, you will need to calculate the volume. They will ask you about the volume. That is the volume of the liquid delivered, the volume of liquid delivered per stroke, just like what we had on a normal hydraulic press. We talked about the volume, so we can talk of the volume there. Thus, we can calculate the volume. All right, so this will be the volume of liquid delivered per stroke. All right, so this is the volume of liquid delivered per stroke. All right, that's delivered per stroke. Delivered per stroke. So that's what you're going to have in the first place. So what is going to be this volume delivered per stroke? So as we know that volume is simply area times the distance moved. So our volume is simply going to be area, which is pi d squared over 4 times the distance. Remember, you're talking about a condition where we have got a plunger. We talked about that part of the plunger where it is being taken up or down. So meaning to say, we must talk about what? About the stroke length. On that consideration, we must be referring on a consideration where we have got the stroke length. So it's going to be the cross-sectional area times the stroke length. All right. That is the volume taken, or the volume that you're going to use. You're going to see that sometimes you might be given a consideration where you are given a certain number of cylinders, this and that. Maybe we are now talking about given maybe, okay, let us just say given C cylinders. All right, the number of cylinders, I'm just gonna put them as C. So given C cylinders, our volume in this case is going to be given as the area, the cross-sectional area times the stroke length times the number of cylinders, which is C. So C is representing what? The number of cylinders in this case. So this is going to give us the volume, which is actually the total volume that you are calculating. All right. So this is one of the things that you need. Also, we've got the part of the work done, and that part of work done, actually, there are so many formulas that you need about the work done. So I'm just gonna list the formulas according to your syllabus, what you need, all of them. I think that can help us because of time. Let us just list them down. Then we'll see what we can do as the explanations go down. So the work done, it's one of the most important parts because we are going to need this. Remember, I talked about when the force is applied at a certain distance, work is being done. So that's the first formula that you're being supposed to think of, from the force times the distance moved, which is we are going to have work done, force times what? The distance moved, which is what? The stroke length. Also, the work done can be given from pressure times the volume. So P for pressure, V for volume. When you are given a certain height, because work done can be given as the potential energy, so it can also be given as mgh whenever you are using the potential energy, or you can have your work done as the volume times the pressure, but we said our pressure can be given as mgh for work done. So instead of that, we're gonna have density, the density, which is pressure. All right, this one for pressure here, we want to take this one, pressure times volume. All right, pressure, remember, pressure can be given as rho gh. So this is rho gh, representing what? Pressure. Remember, I talked about this, that pressure, I'm just gonna use small letter P for pressure, is given as rho gh. That is density times gravitational acceleration times the height. That is the pressure. So these are the formulas that can be used to calculate our work done. And as we know that work done is measured in what? Work done is measured in joules. So you can write this in kilojoules on your conversions. All right. So the P, the small letter P, like I said, is for pressure, V for volume, M is the mass in kilograms, G, the gravitational acceleration, H is the height, V, we talked about this, that's the volume, F, the force which is applied, and S, which is the stroke length. So that is how we can be able to calculate the work done. We shall see more questions as we move on. We shall have questions pertaining this work done. So this is from the work done, which is equivalent, which is actually our potential energy. In this case, this one, it's simply the potential energy, like I said, from mgh, it's the potential energy. Okay, what else? The other part, they can ask you about the flow, which is when we can be given a condition whereby you are given the flow rate, which is the volume per second. That can enable you to calculate the rotational speed. It's another part that is important also. So we can talk of the rotational speed. All right. That is the rotational speed. Just gonna write this as small letter n, like this. The rotational speed, which is taken from what? From the flow rate, all right, or from the rate of flow. So this one is taken from the rate of flow. Q, representing the rate of flow, is equal to the volume times the rotational speed, which is given in what? In revs per second. This is our rotational speed in revs per second. This is our volume in cubic meters. So it will give us the flow rate, which is in cubic meters per second. So this Q representing what? The flow rate, or the rate of flow. So this is the rate of what? The rate of flow. All right. Then N is the one that is representing what? Our speed, which is our rotational speed in this case. All right. So we can make N the subject. That is the rotational speed is equal to, you divide by V both sides. So it is equal to the rate of flow over the velocity. All right. Remember that the rate of flow is cubic meters per second, and the volume is given in what? In cubic meters. So this is going to give us N, which is the rotational speed in revs per second. So you take them as revs per second, all right? So that is the idea. So this N, our rotational speed, is in revs per second, revolutions completed per second, all right? So that's the idea there. So also, the Q that we are talking about here, given like this, is called the theoretical value. The theoretical, this one, because we do not have efficiency. Remember, when we have got efficiency, when there's an efficiency, it means we now have the actual rate of flow. All right, the actual rate of flow efficiency has to be involved. So when the efficiency is involved, Q is equal to the volume times the rotational speed times the efficiency, like this. So this will be the actual rate of flow. So this one was the theoretical, all right, rate of flow. Then this one will be the actual. So this will be the actual rate of flow. That is the idea there. So we have got the actual rate of flow, the theoretical rate of flow. These are the two things that you need to understand. The unit's still the same, cubic meters per second. So the actual, remember I said actual values, we talked about actual values when you're talking about hydraulic press, talking about actual volume, those things, we had efficiency involved. Even when you talk about the weight on the ram, which is the ideal values and the actual values. The ideal values, there was no efficiency. Those are your theoretical values. Then actual values, efficiency is involved. So from this one, we can even make efficiency the subject of the formula if you want. All right. We can even find the formula for efficiency from there. That's the advantage of formula. You see, guys, the advantage of mathematics. It brings you formulas that you can manipulate in favor of what you want. So this is V for the volume. Remember, said this is for the volume, cubic meters. This is N, our speed, which is in revs per second. This is the efficiency. So this is our efficiency in that case. All right, just gonna write it as a decimal, the decimal percentage of it. So that's it. That's it. All right. What is it that they can ask us also here? Maybe you might be given a condition where they need you to calculate time. Yeah, it can be like that. They can ask you to calculate the time taken to fill or empty a dam or a reservoir. Remember, we said we've got a reservoir, the one that water can be taken up or it can be taken down. So you can talk about the time to fill it or to empty it. All right. So you can talk about the time taken to fill or empty, to fill or to empty the what? To empty a reservoir or the reservoir, just like a reservoir there. All right. So what is the time that will be taken? How do you calculate the time to be taken in your calculation? Reservoir, guys, is OIR, isn't it? OIR, like that. All right. So we need the time that will be taken to fill in this part or to empty this. What is going to be the time? That is the question. All right. So considering this part here that all right, let's just do this. Considering that, remember, time is measured in seconds. And here we've got volume in seconds. I mean, we've got the flow rate in a cubic meters per second. That is something that is already carrying time in seconds. So what we need to have seconds is to remove this cubic meters, this one. If we can remove the cubic meters, it means we can have a second. So what can we do to remove this? We must divide. So it must be the total volume over the total flow rate, which is our Q, because volume is measured in cubic meters, remember, and this is cubic meters per second. So this cancels, and we are remaining with 1 over a second. The reciprocal of 1 over a second is what? It's a second. So it will give our time in what? In our seconds, if we play our mathematical calculations well. So this is the formula that you can use to calculate the time taken to fill in or to empty the reservoir, where VT is the total volume of the reservoir in cubic meters, and the Q is the flow rate in cubic meters per second, like I explained before. All right, so this is what we might need. And I talked about the finding of theoretical and actual values, which is fine. And what else? Efficiency. All right, what about also this efficiency? Because we might be given power, but we talked about this, guys. Efficiency, when given power, is the power output over the power input times 100%. All right, that's how you can calculate efficiency, whereby the power output is the power that is this one, P out, is calculated from this one. Let me show you how to have these two powers here, because this formula, some of us, we confuse it. We just know that is P out over P in. So this P out is the output power, which simply means the work done per second. So what does it mean if you're talking about work done per second? Work done is calculated. Remember, we talked about work done. Work done is calculated when given total volume. Work done is going to be the volume, total volume, times what? Times, all right, total volume times the pressure, isn't it? Total volume times the pressure. We talked about this, okay? That is VT times pressure, or P. Let me just write the way that I wrote it before. I just wrote like this, P, which is for pressure, times V. So V is the total volume. This is work done. But we need work done per second. So to have work done per second, it means we are going to divide this. So P out is going to be work done per second, means this is work done. So it's going to be P times the total volume. To have per second, it means what we must multiply by the speed in revs per second. So it's going to be multiplied by N in revs per second. It's because this gives us the work done in joules. So this, for us to have joules per second, we must multiply by something per second. Remember, revs per second, these are not units. Revolutions are just like how many revolutions completed. So we do not have units here. The only unit that we have is per second. So it will give us work done per second. And remember, work done per second, that's like maybe you've got joules per second. Joules per second, it means what? A watt. So if it is kilojoules per second, it's kilowatt. That is the idea. Remember your formulas, guys, from your N3. So this means this one is where we can have our output power. This one. So we have got output power. All right. We can calculate this. Then P in is the power to drive the pump. This one. This is the power to drive the pump. Whenever you're asked to calculate the power to drive the what? The power to drive the pump. This is your P in. That is the power to drive what? To drive the pump. That's it. So in actual sense, P in is simply taken from pressure times Q. That is power to drive the pump. All right. We can have it from the flow rate. All right. We are going to talk about that in our calculations later on as we do our calculations. And as we talk about efficiency, we must also understand the slip also. If there is a slip, therefore the machine or the pump or whatever that you're going to talk about, it is going to have an efficiency which is 100% minus the slip. All right. So if you're given a slip of 5%, then the efficiency of the machine is going to be 100% minus 5% of what? Of this part, which is the slip. That is, we can have efficiency from what? From the slip. All right. That is how we can have this. All right. We said 100% minus what? Minus the slip. I want this part, which is the percentage slip in this case. So this gives us what? Efficiency, meaning to say we can use this in favor of what we want. We can make whatever that we want the subject. All right. So those are, I think, guys, with these formulas, you can be able to calculate whatever that you want. Talking about the total volume, this VT, we talked about this total volume here. If you still remember, when we have got volume here, we said the volume can be taken from these formulas, pi d squared times S, which is the stroke length. But when given the number of cylinders, we multiply by the number of cylinders, all right? Then we talk about the rotational speed from the theoretical rate of flow and the actual rate of flow, depending with what you are given on the question and the time taken to fill or to empty a reservoir or a dam, whatever that you're given that you're supposed to fill or to empty it. And also the efficiency can extend in the calculation of power, which is power to drive the pump, from the power output, which is the one given from the work done per second. Power is work done per second. So if we can calculate work done, it means we just need to have per second, and to have per second, we multiply by revs per second, which is already in revs per second. All right. So we want to check what we have. The first question that we are going to answer is actually an exam type of a question, but that's the introduction that we have. And it's a direct type of a question. We just want to see our applications or formulas from those pressure. They are not changing from pressure. The calculation of pressure, those formulas, they are not going to change. Remember, I talked about this pressure here, and I said pressure, it's even found as rho GH. Also, pressure is equal to the force over the area. All those formulas, they are not changing. It's part of hydraulics. All right. Only that there are some effective formulas that are to be extended depending with the type of a question. Are you dealing with a pump or a hydraulic press? All right. But they are universal formulas which do not change for any part. All right. Let's check our question here. Hydraulic pump question. The force on the plunger of a water pump, take note, of a water pump is 20 kilonewton. So we have got the force applied on the plunger, which is given as 20 kilonewton, that's 20,000. And the work done during a delivery stroke is we are given the work done. So there we have got work done, which is 3 kilojoules. The diameter of the plunger is, we have got the diameter of the plunger there, divide by 1000. This is millimeters. That's 0.15 in meters. We're given the diameter of the plunger. So the question is, first one, 5.21, calculate the pressure during the delivery stroke. What is the pressure during the delivery stroke? All right. Do we need work done there? No. Pressure is just direct, isn't it? Force over area. Yes, we have got here, take note, work done. Remember from work done, we said work done is pressure times volume. It means we need volume here. But if you check, the volume is the one that is asked on the second person. So the work done is not working for now. We are going back to our normal form. That's why I said do not neglect those formulas. They still play a role, a major role, because it's hydraulics. As long a formula can be applied of hydraulics, that formula must be used. So we are saying the pressure is given as what? We could have used as, just going to use small letter P so that we do not confuse when you talk about power. So you could have used rho GH, but we do not have a condition whereby this is vertically up. We do not have height taken. So we are going to take it from the force over the area. So this is force over area. All right, the area on the plunger. All right, so that means the pressure is going to be given as the force on the plunger, which is FP, because we've got force on the plunger, so it's going to be FP over the area on the plunger. That is area, it's pi d squared over what? Pi d squared over 4. So this is going to give us the pressure. So we've got FP, the force on the plunger, 20 kilonewton, that's 20,000, or 20 times 10 to the exponent of 3, over the what? The area, which is pi d squared over 4. So you're just going to substitute. That's pi times the diameter of the plunger, which is 0.15 squared over 4, like this. So this is going to give us the pressure. So the pressure in this case is going to be taken as, okay, that's a big value actually. It's actually 1,131,000. 768,484, something like that, Pascal. Remember, pressure is measured in what? In Pascal. But you can convert to megapascal. This is a million. Guys, a million. 10 to the exponent of what? Of 6. That's a million. So we simply have to divide or multiply the whole part here by the inverse of 10 to the exponent of 6, which is 10 to the exponent of minus 6. It gives you a value which is now in a megapascal. So if you multiply by 10 to the exponent of negative 6, you're going to obtain 1, something, 1,3, 17, and so on, which is 1,32 to 3 decimal places. These are now megapascal. So to convert to a certain unit, you multiply by the inverse of the unit. If you want to convert to kilopascal, you multiply by the inverse of kilo. You multiply by 10 to the exponent of negative 3. The answer that you get, it will be in kilopascals. You just take the answer from your calculator as it is, but that answer will be in kilopascals. Meaning to say, to convert to megapascal, I have to multiply by 10 to the exponent of negative 6. The answer that I get on the calculator, 1,3, whatever that, it is automatically in megapascal. All right? That is the idea there. So that's the pressure. It was just a normal and a direct question, right? Nothing to worry about here. All right. 5.22, the volume of water displaced during a delivery stroke, the volume. Since we have pressure, we have work done, we can calculate the volume because there's a formula here. Like this, especially for work done, I say these ones here, please do by all means to know these formulas by heart. All right? As long as you're dealing with a pump, and also the ones for the flow rate. So if we check there, we've got work done. So using this formula here, taking the work done, the pressure and the volume here, we can calculate the volume, isn't it, guys? We can calculate, because the only thing that we do not have there is the volume. Work done is pressure times volume. We have the pressure. We calculated a pressure here. Work done is there. All right, so that's 5.12. Let us just say 5.22. 5.22. Let us just calculate it here. So we said work done is equal to pressure times volume. And as we want to calculate the volume, that is this V. So how can we calculate V? We are simply going to divide by the pressure both sides. So this cancels. So therefore the volume is equal to the work done over the pressure. So that's the volume is the work done. We have the work done. We are given, remember, that's 3 kilojoules, kilo to the exponent of 3. 3 times 10 to the exponent of 3 over the pressure. This is our pressure here, which is 1,132 times 10 to the exponent of 6. Remember, mega to the exponent of 6. So that's it's gonna give us the volume. So if you calculate this from your calculator, you're going to obtain something like 2,65017, something like that, to the exponent of minus 3. So it's 650 there, suppose it's 0.17, so it's going to be a 0 there, times 10 to the exponent of minus 3 in cubic meters. You can also leave the 0 there. It does not affect anything. So this is the volume that we are going to have in this case. That is the volume that we have. Okay, it was straightforward, isn't it? Okay, so these are your pumps, guys. That's how the pumps are given. We shall see more questions to come. Don't worry. We are still on the basics. 5.23, the stroke length. Okay, we have the volume, so we can calculate the stroke length, isn't it? Because we know that this volume is the volume of the plunger. Remember, if you're talking about the pump, we never talked about the ram. They were talking about the side of the plunger. That's where we talk about the volume. So this volume is the volume that we have on the plunger side. Okay? So this is the volume on the plunger. And we understand that the volume of the plunger is given as what? All right, that's 5.23. Because we want to calculate the stroke length, which is S, and we do not know. But we know that from the volume of the plunger, it is given as the cross-sectional area pi d squared over 4 times the stroke length, whereby this is our cross-sectional area, and as we want to calculate S. So you can make S the subject, that is VP over, divide by the area, which is pi d squared over 4. So that is going to give us what? Our stroke length. So that's pi d squared over 4 like this. So that's our stroke length can be calculated from the pressure, from the volume that was calculated of what? Of the plunger. So we just have to substitute here the volume of the plunger, that's 2,650 times 10 to the exponent of minus 3. Like I said, the 0 is not important here. Over the area, the cross-sectional area, pi d squared over 4. This is the pi d squared over 4, the same pi d squared over 4, this one that we had previously here, pi d squared here over 4. And this was what we obtained, pi times 0.15 squared over 4. So we are just substituting our pi d squared as it is. So that was pi times the diameter. We said 0.15 squared over 4. That is the diameter of the plunger. So this is going to give us the stroke length. And that is going to give us something like 0.14995, like that. So this will be 0.150 to 3 decimal places. So that's 0.150. That's 150 in meters. All right. So this is your stroke length. That is how you're supposed to have your stroke length. It's a matter of manipulating the formula to what you want it to be like, all right? Working with the formula in favor of what you want. That's a formula. That's the advantage of a formula. It can be manipulated to what we want, all right? So playing around with your mathematics also, it is an advantage that you understand your mathematics. Like I said, engineering, mathematics is supposed to be one of the easiest subjects, so that all these parts that you're talking about, it is going to be understandable. So I challenge you guys to revise as much as you can, preparing for yourselves for the exams that are ahead of time. But for now, that's it till we meet again.